Today we are going to look at some reduction and oxidation reactions that apply to organic molecules. We call these kinds of reactions redox reactions. Was a bit of a short form on the names. Let's talk about oxidation reactions first. The definition of an oxidation reaction in organic chemistry, because it does have a different definition when you talk about it in terms of electrochemistry. In organic chemistry, oxidation is defined as a reaction that happens to carbon-based molecules that forms more bonds to oxygen and less bonds to hydrogen. So when we look at these reactions, we are kind of keeping track of how many carbon-oxygen bonds we had and how many carbon-hydrogen bonds we had, and then do they get to be more or less after the reaction is complete. If you form more CO bonds, you're going to have an oxidation reaction. So typically the kinds of molecules that get oxidized in organic chemistry are alcohols, which can be oxidized to make aldehydes. Aldehydes can also get oxidized to make carboxylic acids, and alcohols can also be oxidized to create ketones. So there's a few different options that can happen here. You'll notice that with all of them, they are molecules that have oxygen in them, sometimes single bonded to a carbon, sometimes double. Alkenes and alkynes can also be oxidized, and if this happens, they create diols. So if you have an alkene, let's say, that is oxidized, this is the symbol for an oxidation reactant, then what would happen is where that pi bond is, you would create two OH groups, two hydroxyl groups around that pi bond, and that's what we call a diol. So when we are reacting our organic molecules with these other oxidizing substances, we call them oxidizing agents, and they typically are reactant molecules that have a high amount of oxygens per molecule or per compound. So for example, potassium permanganate, in one compound contains 4 oxygen atoms. That's quite a bit. Next door is potassium dichromate, which has 7 oxygens per molecule. That's a lot. And ozone is also a common oxidizing agent, and every molecule of ozone has 3 atoms. So these provide a lot of oxygens that allow us to oxidize these reactions. So let's go through and show you some of these oxidation reactions, starting with alcohols. So you'll recall in our lesson on alcohols, we had to classify them, and this is where that classification of alcohols comes into play. If you start with a primary alcohol, and I'll start with something like, I'll do 1-butanol, okay? And we know it's a primary alcohol because this carbon-oxygen bond is only bonded to one R group, and we know that there would be 2 hydrogens left over here to bond to carbon. So for 1-butanol, we'll just get the name written here. If we want to oxidize 1-butanol, we have those oxidizing agents available, but we usually just write an oxidizing agent as this symbol. So we put an O with square brackets around it. This is not oxygen, okay? This is not oxygen gas, that is O2. This symbol stands for an oxidizing agent. And what happens is we're going to have that 4-carbon chain maintained, and around the COH bond, we're going to make more carbon-oxygen bonds. And the way to do that is to create a double bonded oxygens. We form a carbonyl, and then we are now left with 1 hydrogen. So we go from a 1-butanol to a butanal, and then we still can oxidize this more because around that carbon, so this central carbon here, I still have an extra hydrogen. And the definition of oxidation is that we make less carbon-hydrogen bonds, more carbon-oxygen bonds. So I still can do this. And so I'm going to add more oxidizing agent, and I will create an extra carbon-oxygen bond. So there's my double bonded carbonyl there. And I'm going to remove the hydrogen that was here, and I'm going to replace it with a hydroxyl group. So I actually end up forming butanoic acid. So with a primary alcohol, you will oxidize a primary alcohol to an aldehyde, and then that aldehyde can keep on being oxidized to form a carboxylic acid. Now let's take a secondary alcohol and oxidize it. So what I'll do is I'll stick to butanol, and I'll put the hydroxyl now on carbon 2. This means that I have a secondary alcohol on either side of that carbon hydroxyl bond. I'm bonded to 2 R groups. So we'll just write in here 2-butanol, and we're going to oxidize it with some sort of oxidizing agent. And again, right around here, I want to create more CO bonds and less CH bonds. This carbon right here is bonded to 1 hydrogen. So I can remove that hydrogen and I can form 1 extra CO bond and get 2-butanone. So I'm going to create a ketone by oxidizing a secondary alcohol. If I keep on adding oxidizing agent, there is nowhere for me to oxidize that carbon any further. There are no hydrogens here. Okay, there's none left. And because there's none left, then I cannot oxidize that site any longer. So I end up with no reaction after forming a ketone. And then if I take a tertiary alcohol, so I'm going to take, well, maybe I'll start off with that butanol again, but I'll put a methyl group here. Okay. So if I take that molecule, and that is a tertiary alcohol because this carbon is now bonded to 3 different R groups, but around that COH bond, I have no free hydrogens. And this is what we need. So in order to oxidize, you have to, exchange a carbon-hydrogen bond for a carbon-oxygen bond. So because I have no free carbon-hydrogen bonds there, I'm not going to get a reaction. So I can supply it with as much oxidizing agent as I want. Nothing's going to happen. The opposite of an oxidation reaction is called a reduction reaction. And in organic chemistry, because again, it means something different in electrochemistry, but in organic chemistry, this now is the opposite reaction to oxidation, which is where we're going to form fewer bonds to oxygen and more bonds to hydrogen. So it's just the opposite of these reactions we just saw on the previous slide. So we can reduce carboxylic acids, we can reduce aldehydes, we can reduce ketones, and a common reducing agent is lithium aluminum hydride. Note quite a few hydrogens per molecule. And hydrogen gas is actually a really good reducing agent, just supplies a lot of hydrogen atoms in order to make the more bonds to it that are needed. So let's do a couple of examples of a reduction reaction. I'm not going to go through all of them because they're essentially just the opposite of what we saw with oxidation. But if I started with a carboxylic acid, let's say, so let's do propanoic acid like this. If I was going to reduce it, then the symbol for a reducing agent is a hydrogen in square brackets. And what we're going to do is around this carbon right here, we're going to make more CH bonds and less CO bonds. So these molecules tend to lose the single bonded oxygen first, and we'll go down to an aldehyde. And we can keep on reducing this because I have 2 CO bonds left, and I could make an extra CH bond. So if I keep reducing that, I will just end up with my primary alcohol, and I'll have these 2 extra hydrogens that have been added in from the original molecule. Now, I do want to mention here that there are some extra products that get created with an oxidation reaction and a reduction reaction. And I'm not showing them here. I'm only focusing on the organic molecule. So be aware, like if you're looking at this and you're like, the atoms don't match up or they add up, it's because there are other products being made, but these are the main products that we want you to focus on. If I take a ketone, so I'll take 2-pentanone like this. Again, if I reduce it, I can create Still maintain 5 carbons. I want to make one less CO bond. So I had a double bond. I'm going to go down to a single bonded oxygen, and then I would make an extra CH bond there as well. And that's it. I can't go any further because I don't have any extra CO bonds to reduce. So there's some examples of oxidation and reduction reactions for you in organic chemistry.